Right, Chapter 5, Electrons in Atoms. Let's do a quick review of what we learned in Chapter 4 about the history of the atom. We had Democritus. He came up with that all matter is made of particles. Aristotle disagreed with him and said that empty space cannot exist. Dalton then came along and said matter is made up of atoms, is the indivisible and indestructible. There are different matter for different elements. We can combine the elements in whole number ratios, and he explained the conservation of mass. Then we had Sir William Crookes come along using the cathode ray tube to determine that we had the stream going through there were charged particles, and then they learned that those were negatively charged, and we called those electrons. Millikan came in and determined the mass of those electrons using the oil drop experiment. Thomson used the plum pudding model, thinking that there was a uniform arrangement in the nucleus. And Rutherford used the gold foil experiment to determine that the atom, the center of the atom, the nucleus, is positively charged and everything around the outside is negatively charged. Chadwick then showed us that we have neutrons within the nucleus, and those had no charge. This chapter, we are specifically looking at electrons. And we are going to look at, in section 1, the light and quantized energy of those electrons. Okay, so in section 1, the objectives we're trying to meet: compare the wave and particle natures of light, define a quantum of energy, and explain how it is related to energy change in matter. Contrast the continuous electromagnetic spectra and the atomic emission spectra. Okay. New vocab that we're going to learn: electromagnetic radiation, wavelength, frequency, amplitude, electromagnetic spectrum, quantum, Planck's constant, photoelectric effect, photon, atomic emission spectrum. Main idea for this section: light, a form of electronic radiation, has characteristics of both waves and a particle. Okay, so remember Rutherford, he did the gold foil experiment, and he determined that the mass is concentrated in the nucleus and that it was positive and that the electrons moved around the outside. Okay, this model did not explain how the electrons were arranged, just that they were outside the nucleus. Okay, the model also does not explain why negatively charged particles aren't pulled into the positively charged nucleus like the opposite ends of a magnet. Okay, so we still needed to figure that out. In the early 1900s, scientists observed that when you heated up certain elements, they gave off light. So think of when you have a piece of metal and it gets really, really, really hot, it turns from a brown or a gray to a really bright red. They were very interested in this. Okay, they wanted to analyze the light that was emitted from that, and when they did, they realized that elements' chemical behavior is related to the arrangement of the electrons. So the light that it emits when it gets warm is related to the arrangement or the energy in those electrons. Now, please take a minute and pause the video and go watch this YouTube video and then come back to the notes. Okay, so what you just saw in that video was the elements. Grab my periodic table. You saw the elements lithium, sodium, and potassium in water. Okay, what happened? They were very reactive, but they got more reactive as they went down the periodic table. So they all reacted in the same way. They all have similar properties because they are in the same column in the periodic table. Now, This alkali metal column is the most reactive in the periodic table, and it gets most reactive as it goes down. So what element do you think is the most reactive? Answer is francium. All right, so you notice that when those elements hit water that they gave off light. Okay, so we're still studying that light. Okay, so we need to go into a little bit of physics here. Visible light is a type of electromagnetic radiation, a form of energy that exhibits wave-like behavior as it travels through space. All waves can be described by several characteristics. Okay, now, first of all, go to this website, or excuse me, pause the video again, go to YouTube and watch this on the different types of waves, and then come back. Okay, two types of waves, and you probably learned this in middle school and probably in Mr. Cradaville's class. You have primary waves and secondary waves, okay? The primary waves are compression waves where the slinky pushes together, okay? And you can see the wave as it passes back and forth, okay? That was the first one that they showed you. The second one, or a secondary wave, is at right angles. This is the type of wave that light waves are. It goes up and down. That's what we're going to focus on right now. Okay, so the characteristics that we use to describe a wave are the following. We have the wavelength, we have the frequency, we have amplitude. Okay, a wavelength, or this little symbol we use for wavelength, is called lambda. The shortest distance between equivalent points on a continuous wave. Frequency is the number of waves that pass a certain point in a given second. Now, frequency is how fast it's going, so it's a velocity. Think about your favorite radio station. I'm just going to use 92.7, the country station in Norfolk. Your radio is actually set to 92.7. That is its frequency. That is how the waves are sent out from the tower to your radio. So basically, when you dial in a number on your radio, you're dialing in a frequency. Amplitude, that is the height of the wave. So let's go here in just a second. We'll go to a picture of this and talk about them. This is really, really important down here. Down here. Oops, let me go back. Sorry about that. Lambda, or wavelength, and velocity. These two, wavelength and frequency, do not affect the amplitude, how high it goes. Very good test question, so remember that. Okay, so wavelength is from crest to crest, from top to top, or from bottom to bottom, trough to trough. That is one wavelength. Okay. Amplitude is how high the wave gets. So this would be amplitude, this would be amplitude, this would be amplitude. Frequency would be how many wave crests pass through a certain point out in a second. So here we could count how fast, how many waves are going, or how many crests of the wave are going through there in a specific amount of time. Okay. Here we have two separate waves, okay? Remember, c is the speed of light. It doesn't change, okay? This is a constant, 3.0 times 10 to the 8 meters per second, okay? Now, look at this red one. You can see that the wavelengths are spread apart. They are longer than the purple ones, okay? So we have a lower frequency. Lower frequency. Purple ones are pushed together, shorter wavelengths, higher frequency. So, when wavelength increases, velocity decreases. When velocity increases, wavelength decreases. Okay? So you can go back and look at the picture before. The red one, the longer the wavelength, the lower the frequency. The longer the wave is, the less waves that you have. Now, Looking at the violet one, the shorter the wavelength, the higher the frequency. Okay, so the more waves that you have, the higher your frequency.